Hi everybody, Mr. Sharkey back with another exciting chemistry video. Today we are in our blue notes packet looking at this page titled Quantifying Energy. We spent a lot of time now looking at energy changes. We did the icy hot lab where we melted some ice and saw the temperature changes over time. We spent a lot of time looking at heating and cooling curves. We watched some Eureka videos that go into a little bit more detail about the differences between heat and temperature. And today we're actually going to start jumping into the calculations that we need to make when we want to figure out exactly how much heat or how much energy has entered or left a system. So to start us off, there are four different things that we need to consider whenever we're looking at an energy change. And these different factors are what can cause changes in these calculations. So the first thing, if you think back to the beginning of the unit, we looked at melting ice on two different plates. And we determined that those two different plates were different substances, and that those two different substances caused the ice to melt at different rates. So one of the first things that's going to matter when we're thinking about energy is the substance that we are discussing. Whoa, I don't know why my iPad freaked out there, but hopefully that doesn't continue. So we need to look at, okay, it's a little cursed, I guess. We need to look at the substance itself. So we could ask ourselves, is this substance water? That's usually the case. Is it some metal that we're looking at, or any other substance we can think of? But every substance is going to accept and release energy at different rates. So that's the first thing we need to ask ourselves. The second thing is that the phase of matter actually matters. Nice. But the phase of matter is something for us to consider as we go through these types of questions. So that's going to be the second question that we need to ask ourselves. So that means if we're talking about a solid or a liquid or a gas, all of those components can change the way that energy or the rate at which energy enters or leaves the system. The next thing goes back to the Eureka video, and that is the mass of our substance or the amount of matter. So if I have the example they gave us in the Eureka video was that bucket with 50-degree water versus a small teacup of 100-degree water. Even though it sounds like that small teacup has a lot of heat in it, it really just has a lot of temperature, and that's because the bucket has a lot of particles that are moving kind of fast, whereas all the particles inside the teacup are moving very, very fast, but there's only a few particles comparatively. So the mass is going to be significant. And then finally, for part four, it is the change in temperature that is going to matter. So for instance, if I want to raise the temperature of a substance just a little bit, I'm going to need less energy. If I want to raise the temperature of a substance a lot, I'm going to need more energy. So these are all the different factors that we're going to be looking at. The substance itself, the phase of matter that that substance is in, the mass, and the change in temperature that we are observing. So when we want to actually start doing these calculations, there are a few different constants that we're going to use. These constants are helpful because they're going to help us set up the proportions that we're going to do for our actual math questions. But as we're looking at these constants, I want us to think about them in a few contexts. The first, I want us to think about where they would show up on a heating curve, because that's always going to be the visual representation of the problem, and it's going to help us keep track of where we're at. So number one, where do these constants show up on the heating curve? Number two, I want us to think about them in terms of a for every statement, because I think being able to verbalize these numbers is going to help take the math problems and give them some context so that we actually understand what we're looking at. So for each of these, what I'm going to do, since I have the magic of my iPad, I'm just going to draw a rough heating curve. This is for water, so we'll assume my melting point and boiling point are 0 degrees and 100 degrees Celsius. I'm going to try to draw these as similar as possible, but I'm only human, so they're not going to be perfect. But I'm just going to draw each of these heating curves, and then I'm going to highlight the relevant area for each of my constants. So I'm just drawing these first four sections because it will cover solid, liquid, and then the phase changes melting and vaporization. And as we go through each of these constants, I'm going to talk a little bit about what they are and when we need to use them. And then we'll actually go ahead and phrase them in those for every statements. So starting with the heat of fusion. The heat of fusion, I also like to think about it as the heat of freezing, because that F, a lot of us don't really know the term fusion, but we do know what freezing is, and that is when our when our liquid becomes a solid, or the opposite. Melting is when our solid goes back to a liquid. So that's going to be this area here. Ooh, I feel like my little orange highlighter is not coming in super clearly. Sorry, little projection issue. Let's go ahead and go with blue. There we go. So this blue section, this is where my substance is melting or freezing, and that's when I'm going to use my heat of fusion. If we look at the unit itself, it has this unit J. That J stands for the unit joules, which is our unit for energy. Or in this case, for this unit, the energy we are talking about is heat. So it is the unit for heat. What this tells me, if I try to dive into this heat of fusion a little bit deeper, it says it takes 334 joules of energy to melt or freeze exactly 1 gram of water. So I could say for every 334 joules of energy, I can melt exactly 1 gram of water. And the reason that that's helpful for us is because we could always set up a proportion where we take our 334 joules per every 1 gram. Sorry, sometimes my J's look a little bit like 5s. And we could set that equal to either the amount of energy that we have in the question over its mass, or the mass with the energy up on top. And then we could go ahead and set up a proportion and solve these questions. So heat of fusion, which also, if you think about it as heat of freezing, that might help some students. And then there's also something called the heat of vaporization. Now, vaporization hopefully sticks out to you as the phase change, vaporization, or condensation. It's opposite. And if you look, its structure is very similar. We have an amount of energy over a mass. Heat of vaporization is going to be used when we vaporize or condense. So that's this purple section of my heating curve here. And if I want to rephrase this as a for every statement, it's going to look very similar. I could say for every 2,260 joules of energy, I can vaporize exactly 1 gram of water. So again, I could take this heat of vaporization, I could write it as a ratio, so 2,260 joules for every 1 gram, and I could set that equal to either the amount of energy over the mass or the unknown amount of energy over the known amount of mass. And I could solve for any of the pieces that I'm missing. So the heat of fusion and the heat of vaporization, they're linked to each other because they both involve these phase changes. On the other hand, we get to the specific heat capacity of solid water and the specific heat capacity of liquid water. And as you look at these units, there should be something that sticks out to you as different right away, and that is that we've included an extra factor down here inside our constant, because now we're including degrees Celsius. The reason that we include this is because we're going to use these constants during temperature changes when we only have one phase of matter. So here I would use the specific heat capacity for solid water when I have solid water, which would be this section that I've highlighted in green. What my specific heat capacity says, it says if I have 2.10 joules of energy, I can change 1 gram of solid water by 1 degree Celsius. So if we wanted to write this as a for every statement, I could say for every 2.10 joules of energy, I can change 1 gram of ice by 1 degree Celsius. The important thing here, this 1 degree Celsius, this is not a starting temperature or an ending temperature. It is always representing a change in temperature. So when we set up and when we try to solve some equations using specific heat capacities, it's very important for us to remember that the only temperatures that go into our proportions are changes in temperature, not the starting, not the final. So if I wanted to set one up, I could say it takes 2.10 joules of energy to change 1 gram of ice by exactly 1 degree Celsius. And I could set that equal to, and again, we might have an energy, an amount of heat that we know. We might have the mass, or we might have that change in temperature. When we write a change in temperature, we usually use this symbol delta, which just looks like a triangle, to represent change, and then the capital T is representing temperature. So delta T is the change in temperature, and that's what we will use anytime we plug in here. This always, always, always has to be the change in temperature, not the starting temperature, not the final temperature. It is the change or the difference between them. So then finally, this last bit here, our specific heat capacity for liquid water. Surprise, surprise, we're going to use that when we have a liquid, which is this section of our heating curve right here that I've highlighted in pink. Again, we have joules, grams, and degrees Celsius. So the amount of energy is going to depend on both the mass and the change in temperature. So I could phrase this as for every 4.184 joules of energy, I can change 1 gram of liquid water by 1 degree Celsius. So if I want to set up and use this constant for a ratio, I would say 4.184 joules of energy are required to change 1 gram by exactly 1 degree Celsius. But on the other side of this proportion, I could either plug in a value for the energy if I know it. I could plug in a value for the mass if I know that. Or I could plug in a value for the change in temperature. Sorry, I'm going to sneeze. We'll take care of that in post. This page doesn't actually go through any calculations, but it walks us through what these constants are and when we're going to use them. So I'm going to stop the video here and give you a minute to take a breather, or maybe you just needed to review what these terms mean and where they come from. But we're going to pause here and we'll make another video where we go through the Icy Hot Lab and actually do some of these example calculations. So if you're going to watch that one, I'll see you then. But otherwise, have a day.